Hi, good morning, folks. Taking a look at the warm-up that's on the board. You're told that you have a reaction with an activation energy of 40 kilojoules per mole and an enthalpy change of negative 60 kilojoules per mole. Which of these four diagrams illustrates that reaction? Mia, what do you think? Okay, everybody, how many people agree with Mia that it's C? Anybody disagree? No. All right, that's correct. This is just basic graph reading, right? You did have to know what activation energy was and what the enthalpy change was on the graph, but hopefully, I hope you get many questions like this on your actual exam. Probably not too many of them, though. But sometimes it is this easy. All right, so today we're going to wrap up the content about kinetics. You're going to have an exit ticket at the end of class today. Part of my attempt to put more things in the gradebook. So be aware of that. Pull out your study guides. And then tomorrow I will give you guys a practice test, and you'll be able to work on those questions in class tomorrow. Next Monday and possibly Tuesday, depending on the situation and which lab I pick, we'll be working on a lab. And then I have not yet decided if I'm going to do the test right after that or if we're going to go over the kinetics sample IA right after that and do the test at the end of the week. We'll kind of play that a little bit by ear next week, but you will have the kinetics test by the end of next week. Okay. All right, so we started yesterday. I'm sure this is on. Yes, okay, good. We started yesterday talking about how do we get these data that we've been looking at, these rate graphs, where we're looking at either an increase in products or a decrease in reactants or something along those lines. So we talked a little bit about reactions that produce a gas. One way we can measure that type of reaction is to collect the gas and measure the volume. And we can do that over time a couple of different ways. One common way is to do the reaction in a closed system with a tube that goes to a syringe. And then as the gas gets collected, the pressure pushes the barrel of the syringe out, and we can measure how much gas we have in the syringe. Another way to do that is by water displacement, like you guys did with the butane lab, where you have, instead of the tube going to a syringe, you have it going into a graduated cylinder that's full of water, and you see how much water gets displaced. So both of those things we can measure at different time points, and we can plot a curve like this looking at the production of a gas. We also, I think, talked about this scenario where we can measure the production of a gas indirectly by measuring the loss of mass, the total mass of the reaction. So we set up a reaction on a balance, and we put all of the entire reaction system, reactants, products, the flask, everything on there to get our initial mass reading. And then we add whatever it is we're adding to the solution, or mix the two solutions, whatever it is. This is showing a very common lab where you take marble chips, which is calcium carbonate, throw them into acid, it produces carbon dioxide. And so as the carbon dioxide bubbles up out of the solution, it gets released, and we put something in the top of the flask that keeps any splashes from getting out, any liquid or solid mass from getting out of the container, but allows the gas to escape. And so once the bubbles are released, that they no longer count for mass on the balance. And so we can measure something where we're measuring the production of the gas by indirectly measuring the decrease in mass. So that is something that we can also do to measure over time. As the experiment is going along, we can track that across time. And typically what we'll get then, either for the production one that I showed you a couple slides ago, or for this one, is you would have reaction rate graphs where we have time and then mass or concentration, whatever, on the y-axis. And then we would have different conditions, which we're going to talk about later. And you would be comparing the effect of these different conditions on the curve, the shape of the curve, and the slope at different time points, et cetera. Another thing we can do that we can track consistently throughout an experiment is we can measure ion concentration, particularly if we have an acid-base reaction. We can measure the hydrogen ion concentration using a pH probe. So you guys measured, when you did titrations from the eggshell lab, you were measuring the pH at a particular time point after the reaction had happened, at the end point of the reaction. So you got a measure of the pH, but or the amount of sodium hydroxide you had to add to get to a neutral pH. Hello. But you weren't able to see it across time. With a pH probe, we can do both. We can measure where a reaction reaches the equivalence point, and we can track it across time. And we'll do some stuff with it. We have a couple of pH probes, so that is available for you to use for an IA. We don't have enough for everybody to use it at the same time. We have some crappy ones that don't work very well that are for the Vernier setups, the data collection setups. I may have Hannah or somebody help me try to get those set up in a way that we could possibly get them to work. I don't know, we'll try. But in any case, this is something we can do, and I will demonstrate this at some point when we're doing the acid and base unit, how this is used. But this is something that you could use to track pH over time, track hydrogen ion concentration over time. We also have some conductivity meters, which could be used also to track conductivity or ion concentration over time. So depending on what you're doing, something like that might be a possibility. We also have a light meter, sorry, Hannah, that we can use to measure luminosity over time if we do it correctly. We learned a little bit last year about how not to do that. But that's also a possibility as well for measuring a rate of reaction. Okay, another thing that we can measure, that we can do, is set up something where we're not actually collecting numerical data, but there's a qualitative measurement. So a very common experiment, and we may be looking at an IA about this next week. I haven't decided which one to do yet, but is a reaction between hydrochloric acid and sodium thiosulfate. It's part of what's called a clock reaction, which is a reaction that takes place over a certain period of time. And a lot of times what happens is, the reaction starts, and then at some point we get a color change, or we get something happening that we can actually visibly see. In this case, it's formation of a precipitate that makes the solution cloudy. And so this is a common experiment to do where you take a piece of paper and you draw like a big cross on it or something like that. You put the flask on top and you look at how long it takes for the cross to disappear because there's too much precipitate in the flask to be able to see it anymore. That is a subjective measure. It is not quantitative, right? So if you can do something like that, but you have to, if you're going to do that, you have to show pictures. You have to figure out a way to make it consistent from experiment to experiment. Yes, Wiley? So I have not had anybody do this specifically. I have heard that it is harder to make this a high-scoring IA, but you can if you do it well. So it's kind of like everything. How you do it and how you write it up is going to be the difference. I don't know if people have done this and gotten like a 22 or a 24 out of 24, but it's relatively simple to do, so that makes it easy. I have not had people do quantitative stuff or qualitative stuff, period, other than folks who basically just did one iteration of an experiment and kind of wrote up what happened, but they didn't have like a whole series of data, and that did not go well. But that also was just, we knew that wasn't going to go well because it was just going to be one trial. So I would say if you can do this well, it is absolutely doable. Okay, and you can absolutely score well with this. Now, where your threshold for well is, makes that relative. And I don't know specifically like what's the highest score that this type of experiment has gotten. But if you're doing something like this, you're also measuring the endpoint, right? You're measuring the point at which you obscure the cross. And so that's really just one time point in the reaction rate. So you're only getting the average rate of reaction. You can't track instantaneous reaction rates. You can't generate a curve like this where you're measuring it at different points in time throughout the reaction. All right, so instead what you would have to do for something like this is you would have to, your data plot would be not concentration versus time, but the time of the reaction on the y-axis would be your dependent variable, and you would have some other condition on your x-axis. This sample graph shows temperature of the solution. So as we increase the temperature of the solution, it takes less time for the reaction to take place. All right, so this would be the kind of thing that you would generate from looking at the kinetics of a reaction just based on the endpoint. You would have to have multiple conditions that you were testing at that endpoint for, because otherwise you just have one data point, and that's not enough. Okay. So yeah, you can measure endpoints of just the endpoint of a reaction, and you can do it with qualitative methods, but it takes a little bit more effort on your part to design a good experiment where you can get a nice a graph of some kind of relationship between variables, and you're also going to have to prove that you were able to do this in some kind of systematic way that was consistent from trial to trial. Okay. All right, now what if you have something that you have to do, that you want to get the time versus concentration or time versus mass or whatever graph, but you can't measure it throughout the experiment. You can't just take the reaction and stick a probe in it and collect data. For example, last year Roger did the experiment where he was measuring the percent copper in brass, but he did it as a kinetics experiment. This is a very common experiment. Different types of brass have different percentages of copper versus zinc, and you can test that by basically dissolving the brass in nitric acid that produces a color to the solution based on how much copper nitrate is in the solution. And you measure that color in a machine that we have called a spectrophotometer that passes light through a solution, and depending on how dark or light the solution is, it will either absorb or transmit more light. And you can measure in a detector what the absorbance is. And then you create a standard curve with known concentrations, and you test your solutions against that standard curve to get the concentration of different samples. The problem is that reaction produces very toxic gases, and we have to do it in the hood. And so we can't do it in the spectrophotometer and test it over time, because everybody would die, and that would really suck. Okay, so we had to do it in the hood, but he still wanted to take different time points. So instead, what he did was had his reactions going in the hood and took a sample of the solution at different time points. Once it's removed from the reaction vessel, the reaction doesn't take place anymore because there's no more brass in there. So you could remove it from the hood, take it to the spectrophotometer, and measure the color of the solution. And so that's another thing we can do. You can take samples at different times. If there's something that you can't measure continuously, you can take samples at different times in order to get those data at different time points to measure the curves. So the lab that I worked in this summer, they did that for all of their new synthesis experiments. Every time they did a new experiment creating a new product, they wanted to test the kinetics of it, possibly at different temperatures, and so they would take little samples at different times and analyze them on the GC or the NMR or whatever it is to see what was being produced at those different times, how much was being produced at those different times. And they would decide if they wanted to slow down the reaction, speed up the reaction, or completely change it because it wasn't doing what they thought it was doing. So that is another, that possibility of sampling and then measuring. And you can measure by titration, you can measure with the spectrophotometer, you can measure a lot of different things of those samples. Typically, when you take a sample of a reaction, especially if it's like if everything is happening in aqueous solution, you don't have like a solid, like in Roger's experiment, you would want to quench the reaction, you want to quench your sample so that reaction isn't continuing to take place in your sample tube. So you would usually put it on ice or put it in a cold water bath or something to slow the reaction down so that you were getting the right thing at the right time point. And it wasn't just continuing to react in your sample tube. So that's also a possibility. All right, so we've talked a little bit here and there about factors that affect rates of reaction. This is a very common kind of IA topic. You usually want to do something, try to do something interesting with it, because a lot of the basics have been done to death, but it is something to kind of help frame your thinking, things that can affect the rates of reaction. So the obvious one, and this is, page 9 in your study guide, and the next couple of pages in there are going to walk through these more or less in the same order. There's a little bit of a difference here. But there are several main things that we can talk about that affect the rates of the reaction. So temperature is the obvious one. If we heat it up, the particles move faster. If the particles are moving faster, they're more likely to collide. So we end up with a higher frequency of collisions between the particles, which increases the reaction rate. With temperature, we have a second effect as well, because we're increasing the probability or the frequency of the collisions, but we're also increasing the effectiveness of the collisions because we have more particles that are going to be over the activation energy threshold. So we're going to have two things happening when we increase temperature. Increase in the frequency of collision, increase in the effectiveness, number of effective collisions, because we're going to have more particles above the activation energy threshold. Right. Temperature is the only one that really changes two things. So that's something to be aware of. You might see a question, either maybe a paper 2 question that says describe the effects of temperature on reaction rate, and it might be for 2 points because they want you to hit both of those points. Or you might see something in one of the multiple choice questions that has the 1, 2, or 3. Which one of these is an effective temperature on the reaction rate? Is it 1 and 2, 1, 2, and 3, 2 and 3, etc.? I've seen stuff like that as well. So remembering the temperature has 2 effects is important.
Would it suffice to say that the collisions are more effective, or would you want, like in a question like that, or would you want to specify that?
I think you would want to specify that they were higher energy to get over the activation energy. Yeah, I think I'd have to look at a mark scheme to be sure, but I think the safest bet would be to talk about the activation energy within that to get full marks for that. All right, next one is question about. Okay, so higher temperature means not only more frequent collisions because of more higher speeds, but also the collision is more likely to be an effective collision that is above the activation energy because the particles have more energy, they're going to collide with more energy, so the reaction's going to go faster because more chances to not only have collisions at all, but then also for each collision to be more effective. All right, next factor is concentration. If we have more stuff, we have more collisions. So the picture here is showing you equal sized chunks of zinc in a hydrochloric acid solution. And we're basically saying this has a lower concentration of acid. There are fewer particles per liter. This one has a higher concentration. The more particles we have, the more frequently we're going to be able to collide with the other reactant. Okay. And so this is just going to increase the frequency. It's not going to do anything to the energy of the collisions, but it is going to increase the frequency and therefore increase the reaction rate. Something I keep forgetting to talk about, I'm going to have to remember to talk about this tomorrow to first period, is that, and I haven't seen it come up much in questions, in question bank questions, but when you're thinking about this, realize that it's the concentration of the limiting reactant that's really going to matter. So taking us back to the horrible topic 1, where we talked about limiting reactants, typically speaking, you're going to put a reaction together and one thing is going to be in excess, one of your reactants is going to be in excess, and one is going to be the limiting reactant. Increasing the concentration of your excess reactant isn't going to do anything because your limiting reactant is determining how much you can make. So the concentration of that is really what's going to be affecting the rate of reaction. So I should really qualify this. Concentration of the limiting reactant. Like I said, I haven't seen any question that gets at this. I'd have to look. I haven't seen any question that like tries to trip you up with that, but it's something to be aware of as you're picturing these things happening in your head. Doesn't matter how much zinc we have. If we already have enough zinc to react to all of our HCl, then it's the concentration of the HCl that's going to determine the rate of the reaction. Yes? Uh-huh. So it has the same thing in terms of it's increasing the frequency of collisions, but it's not changing the energy profile of the collisions. So temperature increases the frequency, but also increases the energy of each collision. So by having more collisions, we're necessarily going to have more successful collisions or a greater probability of a successful collision, but it's not because we're increasing the energy. It's because we just have more collisions, period. And the same percentage of them are going to be effective, but we have more of them. Okay. We can also talk about pressure, and this is a little bit later in your study guide, but I like to put it next to concentration because I think they're very similar. They're very similar in the way we think about it. Pressure affects the rate of reaction if we have gases in our reaction system. Okay, if everything is happening in aqueous solution, pressure has no effect. Okay, but if we have gases, then increasing the pressure is going to do something very similar to increasing the concentration in an aqueous solution. We're going to put more particles closer together. Even if we have the same absolute number of particles, we're shoving them into a smaller space. That's going to increase our frequency of collisions. So that's also going to increase the reaction rate. And you can also think about it, I like this picture better because it's sort of thinking about in the same container, if you were to increase the pressure, you have the same number of particles, but in a smaller space, they're just going to bump into each other more easily. It's a lot easier to have a mosh pit in a small club than in a big stadium. Okay, The next one is it's the same thing, but we talk about it in two different ways. It's surface area and particle size. It ends up meaning the same thing. So surface area, the surface area for the same unit volume is going to increase if we cut it into the substance into smaller pieces. All right, so if we take this volume of this cube, the surface to volume ratio is relatively low. When we cut it in half, we're introducing two whole new surfaces. So we're increasing the surface to volume ratio. If we cut it in quarters, we're increasing it again, and so forth. So the smaller the particles, the larger the surface area. So all right, see you later. If we have a larger surface area, then we have more places where our reactants can collide. If we have a small surface area, if I put this big block of a reactant into a solution, only the outside surfaces can be attacked by the other reactants. Everything inside that block is protected. If I start slicing it up into chunks or grinding it into a powder, now I have all these spaces where collisions can happen. So larger surface area means smaller particle size means faster reaction. Yes?
So, is the faster reaction, does that count as
Changing the frequency. So you can think about how many collisions you can have with smaller surface area versus a large surface area. We're changing the frequency of collisions. I think that's doesn't actually, yeah. Increased frequency. Okay, so this is also going to increase the frequency of collisions. So everything so far is increasing the frequency of collisions, and then temperature is also increasing the energy. Okay. Everything has increased frequency, okay? And then temperature also increases the energy. Okay. What's another thing that we've talked about? I kind of forgot to do this in first period, and we'll see how that affected their exit tickets. But what's the other thing that we've talked about that changes the reaction rate? Catalysts, yeah. So what is a catalyst, the addition of a catalyst, going to do to the reaction rate? It's going to speed it up, yeah. It's going to make it faster. Okay. Well, no, because catalyst is going to change the what? No, well, in some cases it can change the effectiveness, but it's also changing the reaction pathway to lower the activation energy. So none of these things are changing the activation energy. All right? Not even temperature changes the activation energy. Temperature is going to change how many particles go above the activation energy, but none of these things are changing the activation energy. The catalyst is the thing that's going to change the activation energy, and that can be complicated in terms of what effect it has on specific collisions depending on the catalyst. Yeah, but all of them are going to, any catalyst is going to reduce activation energy, not change the total energy. That's the mechanism for a catalyst. Okay. Yeah. So just to review the surface area again. So you have to pay attention to what the question is asking. So if it's asking you, like, what's the effective surface area on reaction rate, you would say the bigger the surface area or the more surface area you have, the faster the reaction. If it's asking for the effective particle size on the reaction rate, then smaller particles make a faster reaction. So just make sure that you're paying attention to that. Okay, so you might generate in your labs or your IAs and or be asked to evaluate one of these diagrams of rate of reaction. So we've got time on the x-axis, we've got mass or volume or concentration on the y-axis, and you might have two different lines from two different conditions of the reaction. And your job might be to determine which line is which condition. So just look, without talking about conditions, just looking at the blue line and the red line, which one is a faster reaction? Blue is faster, right? We are increasing our products faster on the blue line than we are on the red line. Now, they're both getting to the same point in the end. Even the slow reaction will eventually go to completion in this scenario, okay? But the blue line is going to get there faster, all right? You may have to generate a graph like this. You may be given the red line and be asked to draw the conditions that draw something like a blue line based on certain conditions, or vice versa, okay? And this is the time when you are going to put your notes away. So this is 8 points, 3 points for question 1 and 1 point for each part of question 2. Oh, thank you. Nope, just the front. Short and sweet. And it is retakeable. Right, you have the rest of the period.